See, something turned up in the early universe that should not have been there. Tiny, faint, deeply red. And when astronomers tried to explain what they were looking at, the most obvious answer kept failing every test they applied to it. These are the little red dots, and their story is a precise lesson in how a discovery can seem settled for a moment, then unravel the more carefully you look. To understand what made them so disorienting, you have to know where they live in time. The James Webb Space Telescope was built partly to look back toward the very earliest chapters of the universe. When it pointed at regions of deep sky and began resolving light that had traveled for more than 13 billion years, it found galaxies forming, structure assembling, the universe in a state no ground-based telescope had ever clearly seen. That was expected. What was not expected was a population of compact red-tinted objects clustered in a narrow window of cosmic time, roughly 600 million to 1.6 billion years after the Big Bang. Most of them appear concentrated near that 600 million year mark, an era when the universe was still young and the largest structures we see today were only beginning to coalesce. 341 of these objects had been catalogued by 2025. Each one is small, each one is red, and together they form a class distinct enough that astronomers gave them a name: Little Red Dots. The discovery was formally announced in March 2024, and from that moment, the debate about what they actually are has not stopped. At first glance, the color and compactness seem to point toward a well-understood phenomenon. The early universe is known to have hosted active galactic nuclei, or AGNs. These are galaxies whose central supermassive black holes are actively consuming surrounding material, generating enormous amounts of energy in the process. AGNs are bright, they are compact, and in the early universe, dust and geometry can make them appear red because the blue and ultraviolet light gets absorbed before it escapes, while the longer red wavelengths survive the journey. The original reports describing the little red dots identified them as likely examples of early AGNs, each one harboring a supermassive black hole in its core. That explanation had genuine explanatory power. It accounted for the compactness, the color, and the redshift, placing them so far back in cosmic time. For a while, it looked like the little red dots were simply early, dust-shrouded black hole engines doing what black hole engines do. Then the closer comparisons began. Known active galactic nuclei share a set of observable signatures that are not optional. They are consequences of the physics involved. One of the most reliable is X-ray emission. When matter falls into a supermassive black hole, the accretion process produces a corona of extremely hot plasma that radiates powerfully in X-rays. Deep X-ray surveys have found AGNs at substantial look-back distances, and the emission is detectable even when the nucleus is obscured in optical wavelengths. The little red dots do not appear to emit X-rays at the levels an AGN would produce. That absence is not a subtle statistical fluctuation. It is a meaningful departure from what the leading explanation required. There is more. AGNs display a characteristically steeply rising infrared spectrum, a fingerprint of the hot dust surrounding an active nucleus. The little red dots show a flattened infrared spectrum instead, not the steep rise the AGN model demands. And AGNs vary. The brightness of an active nucleus fluctuates as material flows in and out of the accretion zone at irregular rates. Variability is so expected in AGNs that its absence would itself be a finding worth publishing. Among the little red dots, very little variability has been observed. 3 independent signatures, each one expected under the leading hypothesis, each one either absent or significantly muted. That is not a marginal discrepancy. That is the data telling astronomers the initial framework needs revision. Here it is worth being precise about what JWST actually measured and what remains uncertain. The James Webb Space Telescope observes in near-infrared and mid-infrared wavelengths, which is exactly what makes it capable of seeing objects at these extreme redshifts. Light that left the universe when it was only 600 million years old has been stretched by cosmic expansion into infrared wavelengths by the time it reaches us. JWST resolves that light with a sensitivity no prior facility matched. The photometric and spectroscopic data confirming the redshifts of these objects, and therefore their ages, are among the more robust outputs of the mission's early science program. But robustness in redshift measurement does not resolve what these objects are physically. The sample of 341 is real, but it is not yet large enough to rule out selection effects, meaning the survey may be finding a biased subset of a more varied population. The X-ray non-detection is a meaningful constraint, but the sensitivity limit of available X-ray observatories at these distances means some low-luminosity AGN activity could fall below the detection threshold. The spectral and variability data narrow the possibilities without eliminating them entirely. What the evidence supports is uncertainty, structured and meaningful uncertainty, not a solved problem and not a mystery without clues. So, where does that leave the explanations? The leading interpretation as of the announced discovery remains some form of primordial galaxy, possibly one in which star formation rather than black hole accretion dominates the energy output, with the red color produced by dust, extreme stellar density, or an unusual population of stars rather than an AGN. This hypothesis better accommodates the missing X-ray emission and the flattened infrared spectrum. Very dense, compact bursts of star formation can produce compact red sources without the AGN variability signature. The AGN interpretation has not been abandoned. Some researchers maintain that the combination of properties could be explained by an AGN whose black hole activity is somehow suppressed or embedded in an unusually large gas column that modifies all three signatures simultaneously. This is a less parsimonious explanation because it requires a specific and poorly constrained geometry, but it cannot be ruled out with the data currently in hand. A hybrid scenario, galaxies in which both compact star formation and low-luminosity AGN activity coexist, is also under consideration and may be the most honest accounting of an object class that does not yet map cleanly onto known categories. The evidence, ranked honestly, favors compact primordial galaxy over pure AGN, but the margin is not wide enough to call the question closed. The test that could settle this is within reach, and it is not hypothetical. Deeper X-ray observations targeting the positions of confirmed little red dots would either detect emission at AGN-consistent levels or push the non-detection to a limit that makes the AGN explanation very difficult to sustain. The next generation of X-ray facilities being developed for the 2030s is designed with exactly this kind of sensitivity. Additional JWST spectroscopy, particularly targeting emission line ratios that distinguish ionization by young massive stars from ionization by an AGN accretion disk, could independently sort the population without requiring X-ray detection at all. If the emission lines show a stellar ionization pattern, the compact star formation model gains substantially. If they show AGN-like ionization without X-ray emission, a new physical mechanism needs to be proposed to explain the discrepancy. What the little red dots have already changed is the expectation that the early universe was a simpler place. The assumption entering the JWST era was that the first galaxies would be diffuse, irregular, and relatively uncomplicated, seeds not yet grown into the massive, structured systems we observe at later times. The little red dots are compact and apparently numerous. If they are dense stellar systems, they imply that concentrated, rapid star formation was occurring far earlier than models comfortably predicted. If they retain any AGN component, the implication is that supermassive black holes were assembling their mass faster than the standard growth pathways allow. Either interpretation requires the models to change. The little red dots are not threatening in the sense of posing physical danger, but they are threatening to a comfortable picture of cosmic evolution. They appeared where models said they should not exist in those numbers, in that form, at that epoch. And that is a different kind of disruption, not a catastrophe, an instruction to look more carefully. The universe has always been more structured than expected at early times. Each generation of deep sky instruments has found that the cosmos was doing more, earlier, than the generation before it could detect. The little red dots are the latest entry in that pattern. 341 small, red, poorly understood objects, each one a data point in a question the next decade of observation may finally answer. What made them red? What made them compact? And what is powering them across 13 billion years of cosmic time? Those are the questions still open. And the fact that they are open is not a failure. It is exactly what a new telescope at the edge of observation is supposed to produce.